So we are finally ready to fine-tune the model. Here the headline says fine-tuning the model on supervised data. Supervised data is just, jargon, deep learning, machine learning jargon, where supervised means that we have a labeled data set. In our case, it's the spam classification data set. So essentially what we are doing in this section is we are fine-tuning the model on the spam classification data set. So yeah, in the grand scheme of things, we took care of these 7 steps already. So the remaining steps in this chapter are fine-tuning the model, evaluating the model, and then using the model on new data. So if I go to the fine-tuning section, there should be a figure here. And this figure is almost identical to the figure we looked at in chapter 5 when we set up the training loop. So what we are doing is we are still iterating over epochs, where one epoch now is one pass over the spam classification dataset. Then in each for each batch in each epoch, we reset the loss gradients from the previous iteration. We calculate the loss on the current batch. So that would be the cross entropy loss. It's still the same cross entropy loss. Then we calculate loss.backward. So this will calculate the loss gradients that we need for updating the model. And then the optimizer.step method. So the step method of the optimizer will apply these loss gradients to update the weights. And then we print the training and validation set losses to make sure the model makes progress. And yeah, I'm just seeing, that's funny. So I'm just seeing this is exactly the same figure we had in chapter 5. So when I submitted my draft figures for the Manning layout team, maybe the figures looked so similar that the layout team used the same figure also in chapter 6, but there should be a subtle difference. So here in step 8, it should say calculate the training accuracy and validation accuracy, because yeah, our model now, it's not a text generating model. So our model won't write text. It will only return class labels 0 or 1. So it would make sense during the training to calculate the accuracies to see how good the model is at the current epoch, and to also track it over the epochs to see if the model is making progress or not. So yeah, there should be a subtle change here where it says compute training and validation set accuracy. So maybe my figures look too similar and they just copy and pasted it. Anyways, I will let them know, and hopefully they can update this. So what we are going to do now is to implement the training function, and the training function is actually almost identical to the one we used in chapter 5. So I'm just copy and pasting it here, and then I will talk through it. Like I said, it's very similar to train model simple in chapter 5. Now it's a classifier that we are going to train. And I do have something also here, like 2 more lists where we are tracking the training and validation accuracies in addition to the losses, so we can also plot them. What else is new? I mean, everything here is exactly the same. So if anything is new here, I would say check out chapter 5. So then, yeah, if there's no question, you can ignore this for now, because it's exactly the same as we discussed already in great detail. There's only a little change that I annotated here. Here we are tracking the number of training examples instead of the tokens, because here we need the number of examples to calculate the accuracy essentially. So we will not to calculate the accuracy, but when we are plotting things in chapter 5, we looked at how many tokens we have seen. Now we can say how many examples we have seen, because the accuracy calculation happens inside those. So for that, this will already do the tracking internally, like we have defined here. So here we will already also track how many examples we have in the loader. This is really just later for the plotting. Okay, and then like I said, this is just printing the training and validation loss so that we can see whether we are making progress during training. And we do the same thing for the training and validation accuracy, but we only do that for each epoch. So here, this is every so in so many steps, where this is something we can specify, for example, every 10, 20, 50 steps, but we only calculate the training and validation accuracies after each epoch, because that is relatively expensive. And we have an evaluator so that we can say only for 2 batches or 4 batches to keep it a bit cheaper, to make the training loop a bit faster. Because like I said, if we have a large training set, this might take a long time. And ultimately, it's not that important to have a super accurate training accuracy calculation during the training. It's here just for a rough estimate. Later on, once the training has finished, we can compute this on the whole training set. But right now, yeah, it's sometimes useful just to keep this relatively cheap. Maybe do this only for 1, 2, 3, 4, 5 batches or something like that, instead of all the, what do we have, 130 batches, because that would be, yeah, slowing down the training quite a lot. Yeah, so this is our training function. There's one more thing we have not defined. This is the evaluate model method or function. And this function is the same function in terms of the code that we used in chapter 5. We just have to redefine it now because the calc loss loader has changed. So this one is also the same as in chapter 5, but we changed the calc loss batch here. So we only use the last token, and this one is used somewhere in here, right? And so, and then because this has changed based on this, we also have to redefine this one, because if we import it from the previous chapter, it will use the old calc loss loader, which uses the old calc loss batch. So I just recommend for this chapter to redefine this one, and this one. But the code here, you can see it's exactly the same. Okay, so let's execute that. And then we can finally look at the code for executing the training. So what we are looking at here is, so I'm importing the time module in Python. So I'm just using that as a rough estimate of how long the training takes. I just wanted to know how long does it take, instead of using my stopwatch, using Python to calculate how long it takes to execute this training. And so how it works is I'm getting the start time when I started the training. I'm getting the end time. So here's the training function, and then I'm computing what is the end time after the training has finished. And then I compute the difference between the end time and the start time. And so this is in seconds. And then I'm dividing by 60 to get the time in minutes. And I'm just printing this just, for my own curiosity. And so I got about 5 minutes when I was executing this. And this is on an old computer, Mac Mini. A MacBook Air from 2020. And yeah, so it might be a bit slower when I'm executing it now because I'm running the recording, the screen recording, and I'm also running the camera here for the camera recording, all on that small little laptop, which might get pretty hot when I'm running this, but I think it should be somewhere between 5 and 10 minutes. We will see in a few moments. I'm setting the random seed here, so because yeah, for the shuffling of the training set and so forth. We have evaluation frequency 50. That means every 50 steps we will see the loss. And then we will calculate the accuracy of the validation set and training set for 5 batches. Like I mentioned before, to keep it relatively cheap, we will only use 5 batches. And we will train for 5 epochs. And the optimizer is exactly the same that we used before. I think I updated the learning rate a bit. So how I determined this, I was running this multiple times and I was just observing based on the validation set accuracy, what is the better setting. So yeah, hyperparameter tuning by observing the validation set accuracy. And this weight decay is to reduce overfitting. So let's execute this. And I'm just thinking what I could talk about in the meantime. So I do have some bonus material I can maybe show to you. But let's maybe for a few seconds stay with this execution. I just want to make sure that the model is training correctly. So how do I make sure? So I will look at the initial loss and then I will wait for the 50 steps essentially to see what the training and validation losses are. And I want to see that this is going down. And if it's going down, then it's looking good. Then we will keep training this in the background and I will maybe go over some of the bonus material. So let's give it a few seconds here. I think it should not be too long. Just looking at my device stats. So the computer is getting a bit warm, but it is in moderation here. So it should not be too bad, I hope. Here we go. So we have 0.2 and then 0.6, 2.1 and 0.6 and 2.3.6. So we can see the training set loss is improving, the validation set loss is improving. So our settings are good here. Everything seems to be on the right track. So let's keep training, and I will talk maybe through some of the bonus material. So if I go to my GitHub repository here, so I have a bunch of bonus material. By the way, the bonus material is stuff that didn't quite fit into the chapters itself because, yeah, a book can't be infinitely long. There can only be so many pages in each chapter. There are some guidelines by the publisher too. So there are some interesting topics which are interesting but not essential, and some readers also honestly might find them distracting. So I just had some additional bonus material that I'm sharing here. And there were also some questions by readers where I felt like, okay, instead of just writing this answer in an email, let me put together a notebook, upload this so that I can reference it in the future. And so for chapter 6, I have 3 sets of bonus material here. So first, additional experiments on fine-tuning fine-tuning different layers and using larger models. So here, this is quite a lot. So I ran 19 additional experiments. So using the same code you are seeing here in this notebook, I put this code in to this file, and then I made modifications. So it's, I mean, I would say it's a lot here because I'm having 19 different experiments in this file, but I made it so that you don't have to really, unless you want to, you don't really have to read the code. You can execute this from the command line. So for each of the 19 experiments, here I'm showing you how you run the experiment. So for example, this would be exactly the same code that we are running in the notebook. And then, for example, we might want to change the position of the trainable token. So here, trainable token, the first one, so what that means if I go, oh, it's already, no, it's not epoch 2. So let me go here. So here we have the logits, and then we say we go to the last token. And the reason why we are doing this is because of the causal attention mask, like I explained here, that the last token has the information about all the other tokens. The first token only has information about itself. And so what you're looking at here is a control experiment where I'm, only training the first token. So what I'm essentially doing here is I'm replacing this by a 0 where I take this first row. And what we would expect is pretty bad results because, like I mentioned before, the first token only contains information by itself. And so when you run this row 2, we can go to row 2 and see what we get. We get still 78% on the training set and 75% on the test set. So this means that so it is still actually classifying certain cases correctly. Why is that? It might be that in certain cases the spam is like very obvious based on the first token, maybe if it's all capital letters or if it's a $sign or something like that. So there is apparently enough information to make a classification that is better than a random prediction. So we get 75%. For balanced data set with 50% non-spam and spam, we would get or expect a 50% accuracy. So it's actually quite interesting. So the first token contains quite a lot of information, but compared to the baseline here, the baseline is 95%. When we train the last token, of course, it's worse. So yeah, I'm just explaining. So this is a control experiment. I would not recommend it, but yeah, this is one thing to do. Then trainable layer, last layer. So this would be training only the last layer instead of also training the last transformer block. So we can see when we only train the last layer instead of the last transformer block, here this trains the last transformer block, this only trains the last layer, we get only 70% accuracy. Row 4, so I can also just read it from here. Here we are training the last 2 blocks. So remember I showed you this here, this figure, where we looked at training only the last layer, and here the last two transformer blocks. In our code, we only trained the last transformer block, sorry, and last two transformer blocks. In our case, we are training only the last block. What happens in our case if we train the last two blocks? And what we can see, the accuracy goes up slightly, so from 95 to 98%, but also the time increases. And by the way, here, I think I was using a different machine, not the MacBook Air I'm running this on right now. I think I was training this on a GPU, A100, so that's why it's faster. On the laptop, it takes about 5 to 10 minutes. Yeah, so there are all bunch of experiments. Here's an experiment where I'm running it on all. So I'm updating all the parameters instead of only the last two blocks. And you can see there are diminishing returns. So here we have 98%, here we have 96%. I suspect this is because of overfitting, because you can see here the accuracy, the training accuracy goes up, the validation accuracy goes down compared to here. So someone might expect, or I would expect, this is probably due to more overfitting. So we are training too much because the data set is too simple here. Yeah, and you can go through all the other ones. There are a lot of experiments. So there's also a technique called LoRa, which stands for low rank adaptation. Let me, by the way, see how far we are in the training. So we're almost done. So yeah, I encourage you maybe to go through this on your own time then. So there's also LoRa in Appendix E, which is a technique for parameter efficient fine tuning. So here also really nice accuracy. Yeah, lots of experiments. One, I think, important thing I should say is, we will get back to that later. When we prepared the training set, so that's what this longest train stands for. We had 120 characters and we were padding everything to the same length. So that means position 120 is important because that's the token that's trained. And if we have new examples, let's say we get new text messages, even though it has nothing to do with the training anymore, we still have to pad them to 120 characters because we only trained this particular position, token position essentially. And so if you don't want that, if you want to have a variable length, you could technically set the batch size to 1. And if we set the batch size to 1, we don't need any padding. So because in the training set, we did the padding to fill up a batch with multiple examples, and then a tensor needs to have the same row length for each row. So here, if you set a batch size without padding, essentially, you can say batch size 1, and then you won't have padding. You can also here do this with a batch size of 8 without padding. And how I did this is I was so it might be too technical, but I was simulating a batch size with a technique called gradient accumulation. So let me see. I have not prepared anything here, so I'm doing this very spontaneously, but I do think I have gradient accumulation. I do have an article on that. So if you're interested how gradient accumulation works, you maybe want to read through this. So it's simulating the batch size by iterating multiple times but then not using the step and the zero grad. So some people might have wondered, why is this zero grad necessary when we train a model in PyTorch? So why does PyTorch not take care of this automatically for us? Why do we as users have to worry about it? And the reason is that it allows more flexibility so that we can experiment with different things as researchers. And here, if we want to accumulate the loss over multiple batches, we can use the zero grad in the step only every so many epochs. So for example, if I want a batch size of 8, but a batch size of 8 doesn't fit into my computer, it exceeds the RAM or the GPU RAM, I want still batch size 8 because it's a more stable loss, but I might have to do a workaround where I have an actual batch size of 1. I treat the model with a batch size of 1, but then I do only the the batch update every 8 examples. In that case, I simulate the batch size of 8 by not updating after each step. So if that is confusing, sorry, it's also not the topic of this video. I maybe encourage you to check out this article. It will probably be more clear if you sit down and read through this article. I can maybe in the future also make a separate video on this sometime. It's just like a simple trick. Long story short, and this is what I was doing here. So with that, I have still the same batch size that I had before up here, but now I don't have any padding, and you can see actually it's good for the accuracy. So the reason why we are doing the padding is just to keep things simple. In the next chapter, in chapter 7, we will take also a slightly different approach. And so there are more experiments if you are curious. And here are the commands to run these experiments. And then here is also like a write-up where I explain in words what each of the rows is doing and what the baseline is. So the first one is the baseline, row 1, the default, and then versus row 17, I'm explaining what I did there and what it means and so forth. So if you are curious about certain things, why we are doing the things we are doing in this chapter, this bonus material might answer some of your questions, because these are additional ways how you can train it also with larger models, what is the accuracy here, and so forth. So this is one set of bonus material. And then I do also have this bonus material where I'm applying this to a bigger data set. So this is the IMDb movie review data set, where there are 50,000 movie reviews, positive and negative movie reviews. And the task is for the model to predict whether the reviewer liked the movie or not based on the text. And so I'm running the model from this chapter only for one epoch because it's a larger data set. It's more expensive. And then I'm comparing it to a model called BERT. So BERT is, so if I go to the attention is all you need paper. So GPT models, I think I mentioned this before, GPT models, all the LLMs that you're using, like in ChatGPT, Anthropic, Claude, Google Gemini, DeepSeek, they're all decoder modules. So the decoder is what you're seeing here on the right-hand side. So this is the whole transformer architecture, and the transformer architecture consists of an encoder and a decoder. And the encoder, so this was originally developed for language translation. And so here the encoder was encoding the input sentence, creating a representation, and then passing it to the decoder, and the decoder is generating the output text. It turns out that the encoder is not necessary because, as you might know, the ChatGPT models are really good at text translation. So it's not necessary to have this encoder. But long story short, the BERT model, on the other hand, so ChatGPT, the GPT model we implemented, DeepSeek, Google Gemini, and so forth, they are this decoder part. But BERT models are models that are just the encoder part. So BERT models can't really generate text. They are more meant for generating a representation of the text that we can work with in terms of classification and so forth. And so the BERT model I am training here is an encoder. And encoders are traditionally slightly better at text classification. So I'm comparing this GPT model to this BERT model here. And you can see in this case, it's not necessarily true. So this BERT model is actually worse than this GPT model. DistillBERT is a smaller version of that. This is actually quite good. So for some reason, the smaller DistillBERT model is better than a big BERT model. And so here you can see it's almost the same accuracy. There's something called Roberta, which is another flavor of an encoder, and this gets 92.95%. There's actually, a few weeks ago, there was a new model called Modern BERT, which I think is also really great. It's just like a modern version of the encoder. But I'm saying that because if you care about classification, you might want to check out encoder models. Here in this chapter, the reason why we are training the GPT model is first, it works quite well, right? So we see it is actually working quite well. And secondly, it's a good introduction to fine-tuning before we do the instruction fine-tuning in the next chapter. Okay, so this is one more bonus material you might find interesting. And the third one here is a simple user interface if you are interested. Taking the model that we have just trained, putting a user interface around it so you can interact with it similar to ChatGPT. You can write this text here and it will say spam or not spam. So it's just like a nicer interface than our Jupyter notebook. So if you are curious, it's just very simple code here based on Chainlit. So just very simple. Okay, I think I talked for a long time. I see our model finished training. It just took 11 minutes on this computer. It used to be faster. I think it's all that recording stuff I'm running here, but we can see that the training loss went down. It almost went down to 0, which is really great. The validation loss too. So they're both in the same ballpark, which is actually really great. So this indicates that there is minimal overfitting, and the training and validation accuracies are also relatively similar, indicating there's only very minimal overfitting in this case. Here, based on that, we might say there's even no overfitting because validation loss is smaller than the training loss. If there was overfitting, usually we would see the training loss being lower or better than the validation loss. This could also be, though, because we estimate based on the number of batches, and that is, in our case, a very small number. It's just 5. So one question now that I'm thinking about this could also be that you might ask, why do we actually not optimize the training accuracy correctly, directly? So why do we minimize the loss? Why don't we just maximize the training accuracy with a loss function? And that is, the simple answer is because accuracy is not differentiable. So that would require talking a bit about calculus and so forth, how we calculate gradients. But since accuracy is not a smooth function, we can't really calculate the gradients of the accuracy. And that is why we don't directly optimize or maximize the accuracy. So we have now our results. So one more thing before ending this probably very long video is to to plot the results so that we can also visually see them. So here I have a general function to plot the values, nothing really interesting. It's just based on matplotlib, similar to what we have done before. And then let me first plot the losses. So we can see the loss goes down. So I'm just looking at things we were looking at here, but it's always a bit simpler to look at it in a plot so we can see things much more easily, because here we would have to track the numbers and look at them, and here we can see, oh, the loss goes down, which is great, and they stay approximately the same, which is also great. So there's minimal overfitting. The model learns to generalize pretty well. And then let's also look at the accuracies. So here we can see they start off a bit shifted. This again is only an estimate based on 5 batches. So when we calculate the accuracy over the whole training order and validation order, it might look a bit different. But we can see it's relatively similar. So minimal overfitting, some overfitting maybe here, but not too bad. So if we then lastly compute, this might take a while, so let me just start running it and then I'll talk through this. So here we are now computing the accuracy over the whole training set, the whole validation set, and the whole test set. So what it will do is it will use the default parameters for, where are we here? For the num batches, and then we can get an idea what is the actual training accuracy, what is the actual validation accuracy, and what is, most importantly, the tested accuracy. So it might take a while. And then once we have finished that, there is only one more section left in the next video where I will tell you how to use this on new data, but I will do it separately. Let's just stay patient. Maybe in the meantime, coming back to this, Chainlit is just like one way of building a nice user interface. You can run it locally or also remotely, and then have a nicer interface. Because everything in the book here we are doing to understand how the internal work. So if I were to develop an app, for example, I would take a different approach. So in a notebook, it's a great way to have plots and everything in the same place. But if you are developing an application, you might want to structure the code a bit differently. So for example, having Python scripts and in this case, where was I? Sorry, organizing it like I've done here, or even differently. And yeah, here everything otherwise is the same. So I'm defining the path, the tokenizer, and so forth. I'm loading the checkpoint, I'm loading my model that I've trained. And then I have a function to basically execute this. I also should say I'm not affiliated by any means with Chainlit. I just found that this is a nice minimal example. Some other people use Streamlit, for example. Also, Lightning AI has a great litserv library, where litserv is also really, so I used to work with litserv a lot. I still do. It's a very nice, fast way of serving models. So also something worth checking out. It's an open source library. So there are lots of options. Our approach here is focused on looking at the code to understand how things work without using any external libraries if possible, so that we get the maximal understanding. And so the calculation has finished, so I can finally stop rambling on about coding design and talk about the results. So we can see we get a 97% training accuracy, we get a 97% validation accuracy, and 95% test accuracy. So based on this, I would say there is no overfitting, but maybe because that is usually what happens when you use a validation set, I tweaked the settings so much to get a good validation accuracy that I have some slight bias towards this validation set. And if I have a totally unbiased data set, a new data set I have not worked with before, like here, I can see this is slightly lower. It's expected usually because I used the validation set quite a bit when I was, for example, determining the learning rate, the weight decay, and so forth. And that's why it's usually a good idea to have a test set where it's like an independent evaluation. And the same can be said about these additional experiments. So here I am looking at the test accuracy. And if you were to do that and select the best model on based on the test set here, you would again, introduce a slight bias. So in that case, it would be a good idea to have a second test set to evaluate the performance of the final model after you select it based on this test set. And yeah, if you're interested in model evaluation and selection, I did have this paper here that I recommend. I'm pretty verbose there and explain all the different trade-offs and everything that might be a good companion if you are interested in building a classifier. But for now, let me take a short break and I will be back with a next video on using this model in practice on new examples.
Get this book at Manning.com